Okay, briefly, we have 100 individuals. We assume that everyone contacts everyone else once a day. The probability of infection is 1.2% upon contact of a non-immune, non-infected person with an infected person. Now, there are other conditions, and you can read them. The condition lasts 1 day, after which the person that had it recovers and is now immune. Okay, that's pretty much the situation. So, question, how many people are going to be infected after 1 day if initially there are 3 infected and nobody is immune? Well, and you should think through each of these questions before I start talking about the solution, just to get a feel for the problem. Wouldn't be a bad idea to say, well, if we have 100 people each making 99 contacts, which would be the case if you're one of these 100 people, there are 99 other people to contact, and everyone contacts everyone else once a day. So in a day, you're going to make 99 contacts, and so is everybody else. So you're going to have 100 times 99, 9,900 contacts. Now, that's not immensely helpful in figuring out how many new infections there are going to be, because most of these contacts are going to be between the 97 healthy individuals and the 96 other individuals that each of them contacts who are not infected. However, that's not a bad idea to still kind of understand this. Now, you ask your question, well, how many contacts are going to produce infection? Well, there are 3 infected people, so there are 97 non-infected people. They're all susceptible to infection, and they're each going to contact the other 99 people. These people are all non-infected. There are 3 infected people, so each of these 97 people is going to contact 3 infected people, and also 96 non-infected people. We don't worry about contacts between non-infected people, but we do worry about contacts between non-infected people and infected people. So we have how many contacts between infected and non-infected? Well, 97 people who aren't infected, 3 people who are. Each of these 97 people is going to contact each of these 3 people. And 1.2% or 0.012 proportion of these people are going to become infected. So if we multiply 0.012 by 97 by 3, we get about 3.5. Not hard to figure out in your head. 3 times 97 is real close to 3 times 100. That would give us 300. 0.012 times 300 is 3.6. 97 is 3% less than 100. 3% of 3.6, just a little more than 0.1. That leaves us 3.5 infections. Okay, so now we have 3 immune people. Now, this is on the next day now. 3 immune people, because our 3 infected people have recovered and are now immune. 3.5 infected people, and the rest, which is 93.5 people, obviously easily obtained by subtracting this and this from 100, are susceptible. So now we've got a new category, susceptible people. So we have immune, infected, susceptible. What the contacts that we worry about are between susceptible and infected people. Those are the contacts that are going to potentially create infections. So what happens on the second day? Well, you have 93.5 susceptible people, each encountering 3.5 infected people. So there are 93.5 times 3.5 contacts of infected people with susceptible people. So we get 0.012 times 93.5 times 3.5, which I calculated to be 3.8 infected. I was a little off on that calculation, so you might want to repeat the calculation. But now, what do we have? Well, on the next day, on the next day, we're going to have the people who were infected on the previous day, which was the 3.5, and the 3 immune people are now going to all be immune. We'll have 6.5 immune people, 3.8 infected people, and that leaves us, and you can calculate it, 89.7 susceptible people. Again, this isn't completely accurate because that 3.8 was off by 0.1, I believe. So, on the third day, how many contacts are you going to have between immune and susceptible? 3.8 between infected and susceptible. It's unfortunate that immune and immune and infected both start with I. Anyhow, you're going to have 3.8 times 89.7 contacts, and 0.012 of those are going to lead to infection. So you're going to have 4.1 infected people. And now there are going to be 10.3 immune because you get to add the 3.8 that were infected to the 6.5. So starting the next day, you're going to have 10.3 immune, 85.7, 85.6 susceptible. 100 minus the number of infected minus the number of immune. So on the next day, that's going to give you another number. We observe that the number of infected people keeps going up. Now, they can't keep doing that forever. There are only 100 people. Get 4 people a day, you'd run out of people to infect in about 20 days. But we could continue the calculation. And if we do, here are representative numbers of what we get. Now, only a fool today would do more than a few days worth of calculations on their own. You should do a couple more so you're sure that you understand the process. But not being a complete fool, I went to machinery and calculated the number of infected and the number of immune for the next, for the first 30 days. Okay. After 5 days, it turns out the number of infected people peaks. Okay. And beyond this point, the number of infected people starts falling and the number of susceptible people continues to fall. So the number of new infections is going to decrease, and the infections are pretty much going to die out around the 15th day, because after 5 days you have 4.37 infections, after 10 days 2.22 infections. After 15, you have less than half an infection, which means that you've got a 50-50 probability that there won't be any more infections. And after that, the probability of infection decreases rapidly, so it's almost certain that the infection will have died out by the 20th day at the very latest. Although it's not impossible, it could continue beyond that. And your number of immune people keeps increasing because, of course, every time somebody recovers, you get another immune person. Okay, so those numbers go up rather rapidly from 5 to 10 days, but then they go up less rapidly, and then between the 20th and 30th day, they only go up by about 0.27 individuals. So that's kind of interesting, and it'll be interesting to look at these sequences apart from this model. Another comment that I'll add here, we could scale up this model by saying, for example, there are 10,000 individuals. Now, we're not going to say every one of those individuals comes in contact with every other. Let's just say that each person comes in contact with 100 people randomly selected out of the 10,000. Doesn't matter how many. The probabilities and the numbers really govern everything. And we start with the same proportion of infected. We have 100 times as many people, so we'll have 100 times as many infected. And we could run the model for 10,000 people with 300 initially infected, and each person making 100 random contacts. And it might be interesting for you to set that up.